Hello everybody, welcome back. This is lecture 12 and today I am Shannon Ellis. No, seriously, what's going on is that I'm in the middle of doing a midterm for the other course I'm teaching, and my kid has to go to his kinderpod trick-or-treating thing here in an hour and a half. So yeah, I've got no time to actually get you my own version of this lecture. So I'm completely reusing Shannon's slides from the last quarter. I apologize to you deeply because some of this stuff involves the data from the students. So today we're going to be seeing data from the fall 2019 instead of from ULOT. And again, I'm very sorry that Halloween and COGS 118A midterm fell on top of ULOT's data. All right? But without further ado, let's get to some content, okay? So, oops. Right, so today's learning objectives, we're going to look at exploratory data analysis and see why we do it and what it means to do this kind of an analysis, right? Remember last time we talked about descriptive data analysis. Descriptive analysis just is trying to literally describe the data without an agenda, okay? What do the distributions look like? What is their shape? What is their central measure? What is their variability? How can we understand their size or problems with the data set like missingness, right? That's descriptive, just saying what the numbers say, right? Exploratory data analysis is a little bit more. So let's return to the diagram we saw last lecture, right? So we know that if we do things without interpretation, we're in descriptive land, but if we try to add some sort of understanding beyond the raw numbers and their statistics, then we probably are entering exploratory data analysis. All right. Nope. Still learning to use PowerPoint. All right. So the goal is to find unknown relationships between variables you have measured in your data set. Exploratory data analysis can be referred to impolitely as data dumpster diving, okay? The implication when somebody calls it dumpster diving is that when you have loads of data, you can find anything in it, right? Random variability is random, and if you go looking at data that without a hypothesis, without a knowledge of what you expect to see, then you can, if the data set's big enough, you can often find anything you want in it. The same way that when you look up at the night sky where there's not too many city lights and you see the whole Milky Way, you can draw just about any picture you want and connect the dots, and that's how constellations happen, right? So there are no actual Big Dippers and Orion the Hunters in the sky. It's just that there's enough data points and we can draw whatever we would like with them. All right. So exploratory analysis is inherently something that you know might be wrong. All right. Only once we get to the far right on this diagram where we have a lot of pre-existing knowledge about the subject and an expectation of what we should be seeing, that's where we kind of get to the point where we're confident that anything we find out of the analysis might actually be true. But before you can get there, before you can get to doing hypothesis-driven analysis, you need to go through an exploratory stage, because obviously there's always a first study. There's always a first analysis. There's always at some point the first time somebody has thought about a problem and looked into it, okay? So the first step is always an exploratory one. And what that means is you just don't have any confidence that the relationships you find are actually going to hold true when you look at it another time with another data set. Here, let me get my, well, that didn't work at all, did it? Nuts. All right, well, so you're not going to be able to read this, but exploratory analysis is open-ended and designed to verify things that we might have found in unexpected relationships between our measurements, okay? So we're just going to go into the data. We're going to see what pops out at us using a few techniques that are designed to only catch things that are fairly clear in the data and not to find the constellation Orion. Okay? All right, good. So again, you have to explore your data. You have to be one of the blind men. You have to start patting down the elephant and hope that the piece of the elephant you get is at least something you can understand, right? If you're totally fooled and you think it's a snake and not an elephant because you've got a hold of the tail, then you're in trouble. If you're lucky, you get like a juncture of like the hind leg and like some of the stomach, and you get a sense that there's a very big animal here. Okay, right? So that's what you're hoping for with an exploratory data analysis, that you luck into a chunk of the data where you get at least a glimpse of what the true shape is. But you always know that you could be one of the ones that's holding on to the tusks and or like the tail and get some completely misapprehension about what it is that we're looking at. Oh man, I keep doing that. I really want it to go the other way. All right. So we are at the part of exploring the data, right, in our process. Okay, so exploratory data analysis is due to John Tukey, who is basically like the hero of statistics in the 20th century. Okay. Yeah, so what can the data tell us, right? That's what we're after here. We're trying to understand the properties of the data. And again, as I kind of mentioned earlier, the idea is that if you find some patterns, you might find patterns that can enable you to generate a hypothesis. And once you have a hypothesis, you can enter the usual kind of statistical hypothesis testing framework, all right? Which is something that you know nothing about right now, but once you take a couple of stats classes, you will. But until you get there, right, you don't have any idea until you get to a hypothesis what it is you're looking for. And so you're looking for patterns and properties that suggest to you a way to ask the right questions. And that's really what EDA is about. It's about using data to figure out what are the right questions to even ask, right? As it says there, it might suggest strategies moving forwards for modeling the data, okay? Also, it's very good at doing sanity check, right? Exploratory data analysis is definitely part of it, is making sure that the data is what you think it is. Okay, that's a big problem. Okay. Whoops. Again, I still don't have PowerPoint down. I prefer my Keynote. So when you communicate with EDA, clearly this is an exploratory thing. You're not here making an infographic for a high-end magazine, okay? Okay. So the general principles are that we're going to look for missing values, look for outliers. We're going to get some sort of numerical summary and also a graphical summary of the data. And we're going to use these plots and some tables to explore relationships within this, this data set, okay? Man, I'm really not good with this. All right, here we are. So you are already familiar with some of the tools of exploratory data analysis. A histogram is the beginning of everything, right? As I've said in the past, when you first get data, look at the histograms, okay? Look at the histogram for each variable. Sometimes it can be very useful to look at small relationships between variables, like doing a scatter plot as well. So that's a bivariate thing, all right? So a bivariate thing for real numbers would be scatter plots, right, like you see on the far right. But a bivariate thing for a categorical data is more likely to be something like a box plot, okay? So you can do this kind of thing. By the way, guess who invented the box plot? John Tukey. You are right. Yes. As I said, the father of exploratory data analysis. Okay? So if we want to look at things, oh, you don't see my pointer because I'm using a different setup. I'm sorry. So understanding relationships between two variables, you would use a box plot or a scatter plot. Understanding single variables, you're in the univariate kind of histogram world. And the last thing is that sometimes when you have hundreds of variables, there's no way you can look at them. And that happens. So you need some way to try to reduce the dimensionality of the data. And that is typically done by something like principal components analysis or a clustering technique. All right. You've never heard the word principal component analysis possibly before in your life, but you are going to become very familiar with it over your data science career. Let me give you an intuition. Can I do this? Possibly. Here's a coffee mug. Let's see if my little stage light over here hopefully is really, really bright. And maybe you can see. Can I find the right way to do this? Okay. You can see the shadow of the coffee mug on my shirt, kind of, sort of. All right? So principal components analysis is taking a high-dimensional object in 3 dimensions, and by using a technique rather like a shadow puppet, it's projecting a 2-dimensional shadow of the object. Okay, it's taking it from 3 dimensions down into 2. Now, the thing about principal components analysis is that what matters is how you make the projection, how you project the light to turn a 3-dimensional object into a 2-dimensional object, right? If you do it this way, and I apologize that the shadowing is not great on my gray sweater, you get kind of a sense of what a coffee mug shadow is. But if you turn it this way, you get a very different result. And I know, I'm sorry, I'm blocking this. Here, I need to hold it that way, right? So that makes it look like one kind of object, and that makes it look like a very different kind of object. So what a principal components analysis is it's a way of looking at the thing along the axis that is the biggest, the highest variability. Remember when we talked about variability of a distribution? So a principal component is a component with great amounts of variability and not a component with a small amount of variability. Sorry, I'm going to turn it towards the camera. Very little variability, quite a lot of variability. Okay? And so that's what principal components analysis does, but with more math. Okay, let me turn off my stage light there. So, there we go. You have just been PCA'd. So this is a super common thing. For instance, when I work with genomic data, I may very likely take, 2,000 genes, the expression levels of 2,000 genes, and project them down and see what the 3 most variable components are of those genes, right? To be very clear, that doesn't mean that we're going to go from 1,000 genes down to 3 genes. No. What you need to think about is that each one of those genes, so gene 1, gene 2, and gene 3, defines a vector space. And variability of gene 1 and gene 2 and gene 3, what we're doing is we're finding some other vector in the middle, which is the combination of those genes, which is where the most variability is. It's that these things change together in certain ways. And so we're not looking along the orthogonal axes, which are the variables themselves, but along some direction in the middle, which is where all the variability happens. Okay? Again, don't worry, this is not going to be on a test this level. I'm trying to give you a sense of the math before you encounter the math in detail. I'm going to learn to use this, I promise. All right, so The biggest cautionary tale about looking through data and trying to find something is something called Anscombe's Quartet. It is indeed because of somebody named Anscombe that we have these 4 data sets. They are very famous. You can look at them on Wikipedia or many other places. And we have some descriptive statistics. We have that there's 11 data points. It has a mean of 9. It has and the x values and a mean of 7.5 in the y. There's a certain standard deviation. There's a correlation between the two. So it seems like it's a well-described thing. Somebody's given you descriptive statistics of one of the Anscombes. Oh, there is a small problem. And the small problem is not just how I use PowerPoint. So the small problem is this, right? Here's that data. We have something that looks very, very nice. It looks like something you can fit a line to. It looks like there's a relationship between x and y. It looks like it's well described. You would assume that if I gave you these descriptions, mean and standard deviation and a correlation value, that you'd be like, I know what the data looks like, right? I know what this is representing. And the point of the Anscombe's Quartet is that you don't. You don't know. Seriously, Jason? You're going to do this? Because Anscombe's Quartet is 4 data sets, and all 4 data sets have the exact same statistics. The exact same means, the exact same standard deviation, the exact same correlation between the dots. And as you can see, these are 4 very, very different data sets. So it just goes to show you that just because you can describe something does not mean you have uniquely identified it. Every measurement in this world is something that can be used as a tool, but it is not the truth, right? There's no one measurement which tells you the truth. Each one of these measurements are indicators. Okay? Think of like the fact that when your car is starting to go, it's been driving it for a long time and suddenly it starts to kind of feel a little funny. You're like, this doesn't feel like it normally does. Maybe it starts to shake a little bit when you brake. You know this is an indication that something is happening, but you don't know what. It's not a unique indicator. Okay? All measurements are like this. And you always have to realize that metrics are metrics. They are ways in which you have some knowledge of the situation, but not an absolute. Okay. So we're going to explore some COGS-9 data from last year. Sorry. So we're going to do some data exploration of not your data, but, you know, these other people. So remember that the full data set has a bunch of variables. We actually have 30 this year. They had 24 that year. But we just added 6 new ones. So this one is in your responses too, and at some point I will show you your data. The most popular favorite color? Well, the numbers look like this. This just goes to show that data cleaning is most of what data scientists do, right? I mean, how do you deal with free-form responses like this? Well, you have to do some sort of cleanup of the situation. You have to wrangle this. You have to figure out how to turn this into something useful. Okay, here we go. So maybe you have to do something like define a bunch of names of colors. Maybe you can find something like a color lookup table, which defines a bunch of possible color names and produces a higher order representation, like takes all the maroons and so on into red, okay, and takes all the, sunset into orange or yellow. Or you can just do it by hand. At 300 some, we can do it by hand. You guys should start a drinking game. No, you shouldn't. You're too young. You should start a game which requires you to do something silly every single time I go the wrong direction with PowerPoint. Okay. So what about vegetarianism, right? Or the number of years that you have already studied here in the university, right? Well, we can visualize those a little bit better because there were a limited number of responses. They require less wrangling. Okay? But you can see very clearly by using histograms that you can look at stuff. We can start off exploring not just individual variables, but relationships between variables. So now, what is it? Is there something where like tall people have better scores or maybe worse scores? Let's take a look. So you plot height versus GPA in a scatter plot. First thing to ask yourself, is there a pattern you see here? Well, maybe there's only one thing up there on the top right. Maybe it's just that very, very tall people. Oh, wait. This is in inches. 10 to the 7th? Uh-oh. Just like our year, the previous year had some random answers about height that were ridiculous. Okay? So there's one person who got a 125 GPA and is like 12 million, something like that tall. Okay. So clearly bad data. All right. Well, let's try to get rid of this bad data, just like I was showing you the last time round. Okay. So I am also going to warn you that even though there are clicker questions here, I am not going to implement them just because time. But so ask yourselves, can we conclude anything about the relationship between height and GPA from this plot? No, as you well knew, because I was treating it that way just from the last slide, right? I mean, clearly there is noise in this data. Also, I want to remind you that just like we explored last lecture, there are most people down here in the GPA land of California, like to a 4 or a 5-point scale. And then there's clearly some people who are on these 100-point kind of situations. And then we have ridiculous measurement over on this side. So there's nothing to be seen here, right? I need to stop pointing with this pointer that you cannot see. So let's eliminate the ridiculous measurements, okay? We're going to filter out GPA to be less than 25 and height to be less than 200 inches, which is still taller than most vehicles. Right. We get something semi-reasonable now, except for the height, where we have a cluster of heights down here, which is like our one person who put their height in feet instead of in inches. So they had several of those last year. So y'all are smarter than 2019. Okay, well, maybe we... Get it? No, no! Not supposed to happen. All right, I'm going to start to use this mouse the right way. Right, so we can do that. We can filter things out. We can get down to reasonable relationships. We can make tables out of this data as well as graphs. Okay, we can eliminate that other chunk of data, the one where we had people giving their, I'm going to start to curse on screen. Okay, where we had these guys over here, where we had the footers instead of the inchers, so we can get rid of that. And now we get to something which looks like it actually helps us answer a question about height and GPA. We've eliminated ridiculous things. All right, now ask yourselves, at this point, can we conclude anything about a relationship between height and GPA? What do you think? Does it look like there's some systematic relationship, something that you would fit a line through? Okay, you could fit a line through this, but what would that line look like? That line would look like a flat horizontal, right? In other words, there's no relationship where, more height is equal to more GPA or less height is equal to more GPA, all right? So it looks to me like there's no relationship. All right, so maybe we can learn something about families size and what was that other? Relationship between families with siblings and siblings with, oh gosh, I hate this. Yeah, not going to happen. Let's look at the graphs and just see. So, distribution of siblings, nice little histogram. Oh, sorry, pets. That was what was hidden underneath my own face. Pets, right? So, do you have a pet? These are two univariates, right? Do you have a pet? Yes, no. Do you have siblings? Yes, no. Well, we can put the two together, okay? Do you have a pet? Yes, no. And you can color it by has 0 siblings in red or by has many siblings, or at least one sibling, in green. Blue. Aquamarine? Somebody say something. Y'all are so dead in the audience out there. All right. So, yes, indeed. Have we learned something from this plot? Does it look like there is any possible relationship between whether you have a pet and whether you have a sibling? Yes, no? I mean, there's a height difference on the red bar, right? And when you turn it into proportions, right, where what you have is each one of these is about how many. So we have a raw number. Let me go back, actually. I skipped over telling you something. Okay? We have a raw number here. There are 100 people that have no pet and 200 people that have pets. Okay? But we don't care about raw numbers. What we care about is, of those 100 people that don't have pets, what proportion of them have or don't have siblings? Okay? So we turned what was a count into a proportion or a percentage. All right? So now we can compare no versus yes. We can compare has a pet versus hasn't had a pet. All right? On equal terms. All right? So now that's where we get down to the thing where we see some height difference in the red bar. We see that people who don't have siblings are less represented in the pet world. So maybe there's some relationship where having siblings makes it more likely that you have a pet by a smallish amount. But it's certainly something to think about given this data. Maybe something along the lines of, you could hypothesize randomly, people who are, like, if you have some parents who are not into pets, then maybe they are more likely to have only one child, right? Or people who are into pets, like, are more likely to have more children, the other way around. What would one of those hypotheses mean compared to another? How would you go about testing that in the future to see if that relationship actually holds? This is what exploratory data analysis does. It suggests questions that you can go look at. So, from this plot, you can't really understand anything because we're looking at counts. Okay? This plot, we can actually make some inferences about because we have normalized it to proportion. And knowing when to do normalization so you can compare things is very important. Okay. So Where did you grow up? You had two questions about that. One was hometown and one was zip code. So which variable do you think we should use to determine where you grew up? So, well, there's going to be differences when we do that kind of data. All right? So look at the missingness. Zip code data has way more missingness than hometown data. Why do you think that is? Well, hometown is easy enough to write. You can always write something. Maybe in some cases you don't even want to tell us the exact town, but you're just like, I grew up in China. But it's easy enough to represent. However, many places don't have something that really looks like a zip code. Okay? Where is this? So I want to skip that. So zip codes are nice in the sense that in the United States or other places that have postal codes, they map to very small chunks of latitude and longitude. You can exactly know oftentimes how many people fall in those places, and you can plot them. There exist libraries where you say, plot 92104, and it'll draw 92104 on a map. But the problem is, oops, oh, we're still going to go with the good stuff, right? So we can plot by zip code in the data from the students, right? So these are plotting where all the 2019 students lived by zip code. Looks great. Okay. But we have some problems. So not every zip code looks like a string of numbers like the Americans. Canadian postal codes have a very rigid structure. So too do English postcodes, by the way, which I assume there's a relationship. And I think many other countries may follow that model, where there are non-numeric things in a postcode. And we only gave you the possibility to respond with a numeric entry. So anybody from Canada or England, or I'm going to guess anywhere else in the Commonwealth, might not have been able to enter the postcode given that we set numeric data. This is a lesson for data wranglers and data collectors, right? Make sure you understand what you're asking. Like, it's always good to provide structure to people so that they don't give you free-form answers like the color stuff. Remember the color stuff where they like said, I don't know, it depends, right? And you didn't get any information from that answer. So you like to structure their data entry, except for the fact that if your structure doesn't take into account what it needs to, like allowing people to enter postcodes that make sense for their home countries, if you force American numeric postcodes, you have the opposite problem from the free-form color data. Wrong way again. All right. So what if we use geolocation? What if we took the hometown name and we tried to infer where that person was in latitude, longitude? Again, there exist software packages to do this. You can do such a thing. And now we get a more full picture of where in the world, not just the United States, that students in COGS 9 2019 came from. Okay? So what can you take away from this map? So I would say that from this map, you all, come on. All right. So one thing that's notable is obviously we have a high density of Asian students and a terribly low density in the Southern Hemisphere except for in Asia. So that's interesting. You might generate some hypotheses from that, something you can use. All right, so some things that we've learned from our exploratory data analysis. Most of you are first years, most are not vegetarian. Blue is quite popular. There's probably no relationship between GPA and height. more families have the pets, similar rates of siblingship between families with and without pets, but maybe a small bonus, right? That says that perhaps there's some families with that don't have pets, maybe slightly more likely to have no siblings. Zip codes are great for the Americans, but terrible for looking at the world. And you really all do come from all over, but except not very much in the Southern Hemisphere. All right. So when is EDA not the thing to do? Okay. So what are you not trying to do with EDA is actually what we're asking here. Okay. So you don't want to try to identify samples that you can remove, outliers that you can remove from your study after you've already analyzed the data, all right? You're not trying to get to the answer you want. You want to make sure that any kind of outlier removal you do before you try to answer questions. You just get rid of things that look like they must not belong, okay? And again, you have to have really, really good reasons, solid reasons for wanting to remove data. Remember that from the last lecture. Okay, after you've done all that, you've done some exploration, and now you want to go back and remove some data? Well, you probably are doing that because it's messing up your ideas, right? You're like kind of forming little ideas in your head about what this data is telling you, and you're like, that data doesn't belong because it doesn't fit what I think should be true. No. So you're letting your own biases and beliefs into the data analysis when you do stuff like that. You're allowing yourself to see what you already kind of feel like you should see. And you're trying to subconsciously, you're trying to make the answers look more like you expect. Remember the problem with the Millikan oil drop experiment that we talked about several lectures ago, right? Where it took people decades to go from a wrong measurement to a right measurement of a physics quantity that had a real absolute answer, right? And it's because the people in the 20s did the experiment wrong, did a measurement wrong, and they were so famous that nobody wanted to actually, they would say, of course Millikan must have been right. I mean, the dude's a legend, so I must have gotten it wrong. And they threw away data that didn't fit with the idea that the measurement was this level. And it took decades of incrementally of people publishing higher and higher results until they finally settled on what we think is probably the right answer nowadays. Okay? Biases affect analysis subconsciously. Please be careful about that. So that's what all these bullet points are about. If you run a statistical test and see that your p-value is just so close to getting the right answer, right? You don't know what p-values are yet, but we'll talk more about them. And so will stats classes. But trust me, there's like this magic threshold that people talk about, 0.05. And when you get to it, you have truth. Spoiler alert, that's not the case, right? But people see it that way. And they do little things subconsciously or consciously to try to get to having a magic answer. Okay? So that's when you don't use exploratory data analysis. You don't try to just use it to get to what you believe should be the case. You need to use it clear-eyed and not to circularly enhance your data to make your desired answers come out the way you want them. So, oh yeah, the good old, if you torture the data, it will confess. Okay? I think it's pretty clear what we've been talking about so far. Okay, let's do another case study. Exploring Kaggle. Okay, and in particular, this is a data set. So by the way, if you don't already know, Kaggle is a competition for data science and machine learning. Kaggle has a bunch of challenges posted all the time. Many of them have prize money attached to them. If you're the best at doing the analysis or predicting something, then you may win sometimes very serious dollars. Okay? It's a fun place for people to get skills and to practice. So they have a data set about data science, okay, where people in the industry filled out all kinds of things about their jobs. Okay, data looks like this. It has things like gender and location, people's employment status, all these working data scientists or non-working data scientists, as the case may be, what they like to use, etc., etc. Okay, so here's the age distribution of data scientists in this 2017 survey. It looks like the vast majority of them are on the younger side. Okay, in the kind of 5 years post-graduation, looks like roughly where we're at. Okay, what kind of plot is this? Do you remember from what we were saying earlier? A, B, or C? Answer for yourself. Okay, it's univariate. The axes, what do they represent? What is the general pattern? Oh, I shouldn't have given you the lead in, huh? Is there anything funny here? You see those bumps over by 0? Okay. What about this? So what's funny about that? I don't mean the labels. I mean, is there anything weird? Do you think there's any relationship maybe between different identity and non-binary? It's possible. We don't really know. Okay. Now, what does a plot like this mean? What is it telling us? Yeah, I'm not very sure it tells us much, to be honest. While there is a small oomph in the median of the different identities, that's, compared to the rest, that's a very unclear thing. And it's likely because there's a few outliers where people definitely are not 100 years old out here, right? So I would guess there's no difference between gender identity and age group here. Okay. So now we can do things where you look at multiple variables at once. These kinds of grid sort of graphs are often used for exploring data sets. All right. So what you're seeing here is employment status versus subgroups. Okay. So you're able to see that maybe there's many more men, right, than there are women, but anything else is really hard to say because of scale problems. Okay, oh sorry, this is the single data version of that. So you can see the relationship of employment single data, univariate data. You can see a relationship among two datas, except you can't really see anything because, you know, raw counts, there's such huge differences. So again, we take our trick of doing a proportional measure instead. So we look at the proportion instead of the raw counts because there's so many more men than genderqueer. Okay? Well, now we've brought up the data to a way in which maybe we can look at some patterns. Okay? Is there any systematic difference in employment status among the various genders in our data? Well, I will let you dive into that and tell me what you think. Or tell yourself, really, I guess. So, any guesses? It is indeed bivariate, right? Now we're getting into the crazy stuff. All right? Not only is this color scheme making my eyes bleed, whenever you have these grouped bar plots, I get confused. But if you look, it's another way to visualize the same thing we did in those separate bar plots, okay? Now we're having just one big old Uber plot, which has, you know, the employment status on the left side, and the proportion of people who are in that status on the x-axis. Now, to find out gender identity, you have to look at the color of the bar. Can you see a pattern? Is there anything funny about this plot other than its color scheme? Okay. This one's about tools that people use a lot, right? Is there a general pattern? Well, that seems clear. This, my friends, is an exponential distribution. All right, it's one of the distributions I didn't cover the other day. But if you think about what an exponential looks like as a mathematical function, you will see very clearly that this is something which is fairly normal when we're at the world of the rich get richer. Okay? If you look at wealth distribution, something like that, you will see this exact same curve, where there are very, very popular tools like Python, and then there are very, very unpopular tools like SAS JMP. Okay? So there are definitely big winners and lots of losers in a long, long tail. Okay? How did they do it? How did they start learning with data science? Looks like online courses in university are the answer, but there are also a fair number of people that worked at it completely by themselves. So, and even a couple who learned it all on Kaggle. That's pretty interesting. All right, now what are we trying to do? Well, we're after that gender thing again as a secondary variable, but now we're looking at job title. Okay? Job title, these people are all doing data science, but some of them are labeled researchers or a business analyst or even an engineer. Okay? Is there anything about this graph that suggests a pattern? I will tell you that this is the first time where I think that maybe there is a gender pattern, but we still have a problem here because it's in count data. And count data, you know, we have a real problem because there's not many data miners compared to the number of data scientists. Okay? So if we wanted to get better at that, I think we would probably look at a proportion. But that is, whoops, still the first time where I'm going to guess that the proportionality of the bars really do show a gender imbalance between the different job titles. Maybe there's just not very many women who get to be called engineer or database manager, although that's harder down there, compared to those that get a job title like data scientist or data analyst. Machine learning engineer actually looks like a pretty tough one as well as the engineer. So, and that is backed up by my limited knowledge of the statistics of female computer scientists and computer engineers. It is definitely, those are some of the job occupations I know which have had the hardest time getting women into their ranks. Not because women don't know how to do the job, but in a lot of cases because it seems like there is a culture that is against people doing that kind of job with that kind of gender. All right. So what have we learned on our exploratory analysis? These are mostly young dudes. They are roughly age similar across the genders, but there maybe are some differences between gender and employment rates, okay, and where they're employed. There's rich tools and poor tools. People learn in lots of different ways, and there's lots of job titles out there. So some of those things have been very clear. Some of them, like gender imbalances, have weak evidence because we know that we could just be seeing random crap in data. All right? So, that was all the way to the end of the slides, which is good because we're at 50 minutes. So, at any rate, number one, I want to say thank you for putting up with me teaching poor slides that I've hardly seen. Number two, I want to emphasize a little bit of story here at the end. It's for those of you that have managed to make it all the way through that presentation. Okay? exploratory data analysis is in fact a really big chunk of most of the analysis you will do as a data scientist. Very rarely are data scientists brought in to ask questions where there's a really huge amount of knowledge and a model and a hypothesis. All right. Oftentimes, data scientists are thrown into a situation by a company that wants to know, like they have those dumb questions where you have to get them into a good data science question, right? They have a question about how can we increase our sales? Well, you don't know anything about their sales yet. So we've got to dance into the data. We've got to dumpster dive a little bit, try to find some things that suggest a way forward, and then design something for that company, some sort of test that they could do to see what are ways we could increase our sales. All right. So somebody with a job title data scientist is very likely to spend a large proportion of their time in the exploratory world. The tools of exploratory data analysis are designed to help prevent you from getting stuck into the hair on the barbershop floor. Okay? What you want to look at is, in a barbershop, is there a lot of hair on the floor or a little hair on the floor? Those are things which might tell you something about the barbershop. But the exact pattern it's arrayed in is worthless. It's random. Okay? So that is, by the way, what would a lot of hair on a barbershop floor tell you? Problem solvers. Get your thinking caps on. Do you want to go to a barbershop where there's little hair on the floor or lots of hair on the floor? This is a classic puzzle, actually. In a modern world, maybe this isn't a truth, but if a barbershop is too busy to clean up the hair on the floor, they're probably a good barbershop because they're popular, right? Okay, at any rate, the point is that the pattern is whether there's lots or little. And that's what the tools of exploratory data analysis are aimed at. They're trying to find big picture stuff that's blindingly obvious. So that's why histograms and box plots and things like that are such important tools, okay? Because they let you see the big picture stuff. You can kind of see that maybe there's like an imbalance where there's like a little bit more people that don't have pets who have no siblings, okay? But it's not clear. That could be the pattern, the exact nature of where those hairs are. It could just be random chance. That pattern is so small, but it looked like it might be true, so maybe you could design an experiment to find out more about that. Okay? So that is the kind of stuff that we've been talking about this whole time. I hope that you have gotten something out of that presentation, and I hope to see you all next week with a brand new installment of slides that are actually mine. All right, bye-bye.